In this lesson, we'll be reviewing the scientific method. I'm fairly certain that most of you have seen this before in your previous high school and middle school classes. However, we're going to be looking a little bit more deeply into some of the terms. So first, we're going to work together as a class to fill in the steps of the flow chart that I've included in your notes. Then we'll go back over each step and really think about the deeper meaning of the terms. The goal here isn't to memorize definitions, it's to understand how scientists think when they are solving a problem or answer a question. By the end of the lesson, I want you to see that the scientific method isn't just something scientists use in research labs, it's a way of thinking that people use every day when they're trying to figure things out. So here's the first step in the flow chart. I'm just going to go back over the different terms. So the title is the scientific method. The very first step is we have to make some observations. You can't start asking questions about what's going on if you haven't noticed anything already. So you could say, well, I planted a garden last year, and one end of my garden, my beans grew great, and at the other end, they didn't do so well. And so my preliminary observations would be the fact that my beans did well on one end, but not in the other end of the garden. So your observations can consist of two different types of information. It can either be qualitative data, and this is going to be information you collect with your five senses. There's no numbers. So by saying my beans didn't do very well, I'm just kind of giving a very qualitative description. And then there's quantitative data. That would be data with numbers. And so if I said that I planted 10 seeds in the bad end and only 2 of them came up, that would be an example of quantitative data. And so the next thing you do is you ask a question. And the question is going to be something that combines the observations together in some fashion. So you could say, well, I wonder what it is about my garden that's causing one end to be better than the other end. So the next step after you have your question, this is where you're going to make a hypothesis. And this is just where you make an educated guess. A lot of people think the scientific method starts right away with a hypothesis, and it doesn't. You have to make observations first. A hypothesis should be a testable explanation for the question. If I said, well, I think fairies are coming out at night and sprinkling dust on one end of my garden and not messing with the other end, that's not very testable. Hopefully you know that fairies are not reliably scientifically. So it should be something like, I think that my plants aren't getting enough water at one end because they're under a tree. So you would say, well, if I make sure to water both ends of the garden, then my bean plants will do better. So that would be my hypothesis. Once you have your hypothesis, then you want to design an experiment that will test the hypothesis. There are various parts to an experiment, as we can see with all of these arrows over here on the side. So you have things like the materials that you're going to need, the procedure that you're going to follow, some new terms, or maybe not new, but terms that people get confused a lot would be constant and control. A control is a basis for comparison. So if I'm talking about living organisms in particular, I need to have a sample that I haven't done anything different to, so I know how big the bean plants would get if I didn't change how much I was watering them, or if I didn't change the amount of fertilizer that I was using. The other one that people confuse with control is constant. Constant is going to be the same for everything that is involved in this experiment, including the control. Then we have the other two terms that people tend to get a little bit mixed up. We have the independent variable. This is the one that the experimenter gets to control. They get to make decisions about it. And if you're looking at a graph, this is particularly important if you're like taking an ACT type test, because this is a favorite question of theirs. It's going to be whatever variable is listed on the x-axis, because that's the rules for making a graph. You have to put the independent variable on the x-axis. And then the dependent variable is the one that gets measured during the experiment. And for the ACT test, this would be whatever it is whatever you see on the y-axis. All right, so we've gone through, we've done our experiment, we've collected all of our data. Another step that a lot of students leave out is that you have to analyze the data. You can't just, collect a bunch of numbers and say, all right, my experiment's done. You have to do something with it. You have to graph it. You have to look for numerical trends. You have to do something with it. You can't, it's just a bunch of numbers on a page aren't very useful. All right, so I couldn't fit it all into one slide, so we've got a continuation here. The next step it's called a decision box in the flowchart. And so we want to know whether our hypothesis was supported. Was our hypothesis correct? Most of the time when you're doing applying the scientific method and doing science, you get a no. It doesn't mean that you did it wrong. It just means you didn't find one of the key factors that affects it. When I was in graduate school for a total of 7 years. The first 4 years nothing worked. It was essentially 101 ways not to achieve what I was trying to do. So what you do, you don't just give up in that case. Instead, you're going to revise your hypothesis. All right, so it didn't make any difference with the water for this hypothetical situation. So I'm going to change the type of beans that I use. I'm going to try a whole bunch of different types of bean plants. Then you have to redesign the experiment, make sure you're now testing the new hypothesis, and go through the loop again. After a couple of rounds, you'll finally get hit on the right combination, and you'll get a yes, your hypothesis was correct. You repeat the cycle a couple more times to make sure that your results are reproducible. And then you are ready to draw your conclusion for your experiment. A conclusion is very specific. It is just for that one experiment. So you could say the addition of this much, 10% sand to the soil will improve the growth rate of bean plants, for example. So you draw your conclusion, and then ideally, if it's a really neat new discovery, you report it to a bunch of other people. They get excited and they start doing their own types of experiments. And after a while, you've had a whole bunch of different people doing different types of experiments. You can formulate a theory. Now, a theory is more general than a conclusion. It's based on a lot of different experiments, looking at a lot of different things. So it's a general explanation of a principle of nature. So looking at bean plants, it would be plants need to have a certain proportion of nutrients in the soil in order to grow. So that would be, and maybe mention some of the necessary nutrients in your theory. And then lastly, it's not really exactly the next step in the scientific method because theories can always be changed once you have more information. Say somebody does an extra experiment and they discover, well, that nutrient is absolutely useless when it comes to growing this type of bean plant. So then you go and you revise your theory and make it so that it's a little bit more applicable to everything that's involved. Scientific laws, on the other hand, is something that is true all the time. There are no exceptions. So like we have the Newton's law of gravitation. It's a scientific law. It says that if you're on a large body of matter, if you let go of something, it will fall. That's all it says. There aren't any exceptions to that. All right, so this next part is just an understanding check. So these wooden things or these brown things at the bottom are supposed to be planters for plants. So each planter is going to get 3 bean seeds, 1 kilogram of topsoil, the same kind of topsoil, 10 hours of sunlight per day, and 100 milliliters of water per day. Into the first planter, we're not going to have any fertilizer. And into the second planter, we're going to put 5 grams of fertilizer A, and into this last planter, we're going to put 5 grams of fertilizer B. So now thinking about the parts of the experiment, that's all this is checking. We let the experiment go, so our beans grow. And so now we're going to identify the different parts. So we look at this list of things up at the top. Notice that it says each planter gets that, even all of them get the same thing. So that means that those are the constants. The first planter didn't get any fertilizer at all, and that told us that the beans will grow to this height, looks like 5 units. I don't know what that was supposed to be. So since it didn't get any fertilizer, that would be the control. Then we have the dependent variable. I'm trying to suggest what it is by the placement of the text. It's over here by the ruler. The thing that was being measured during this experiment was the plant height. So that's our dependent variable. And then the independent variable, the thing that the experimenter got to control, was the type of fertilizer. All right, so the problem with the way the scientific method tends to be presented is that it makes it seem like only people in research labs wearing lab coats with the funny eyebrows and gray hair, they're the only ones that ever actually use the scientific method. One of my personal agenda items, and I'm sure this is true for most science teachers, is to convince my students that they all use the scientific method all the time. They just don't think of it that way. So I have an example of real people out in the real world using the scientific method to solve a problem. There is a little bit of artistic license involved here, but not too much. And yes, this really did happen. So during World War II, Allied forces established a number of air bases on islands in the South Pacific. The influx of material goods improved the living conditions of the native islanders. So there's the island with the islander. Times are kind of tough. Military shows up. They put in a runway, put in a control shack, and then the airplanes start arriving, bringing with them all of the material goods that they need to support the military base that they're building. Now, of course, since the islander also lives there, he also benefits. So his lifestyle has made a dramatic improvement. And then the war ends. Military people go away, taking with them all of the goodies from the military base. So he says, aha, I'll apply the scientific method. So the first step, make observations. Airplanes bring good thing to the island. The airplanes didn't appear until after the man started sitting in the shack, and then the airplanes disappeared after the man left. Step 2, formulate a hypothesis. If we put a man back in the metal shack, the airplanes will come back. So step 3, design an experiment. The man needs a table to work at, a chair to sit on, and those are supposed to be coconuts. And he needs to be wearing coverings over his ears. Apparently this was very important. Step 4, collect data. So he says, I wonder how long it'll be before the planes come back. So he's going to measure time. So 30 days later, he's looking a bit discouraged. He says, this isn't working. And so we go on to the next step of the scientific method, revise the hypothesis. And in truth, the islanders did revise their hypothesis. They would weed the runway. They would put lanterns out on the runway. They kept fiddling with the fake headphones on the mannequin, trying to attract the airplanes to come back and bring with them all the material goodies. Now, of course, there was a fundamental flaw in their whole experiment in that hopefully you know that was not enough to make the airplanes come back. All right, so typically what I do is I have people write a little paragraph on how they used the scientific method in their own lives. And so it says to write at least one paragraph describing a situation in which you applied or attempted to apply the scientific method to solve a problem in your everyday life. Be sure to explicitly state your hypothesis, the results of your experiment, which would be the data collected, and any conclusions that you were able to draw from the data. And finally, answer the question, what would you do differently if you were to do it all over again? So the example I usually give for this is I say, well, you could say, my dog likes stinky food. My dog ran away. I put stinky food out on the front steps. My dog came back. Not super exciting, but it does demonstrate that you understand how to apply the scientific method. I've had a lot of people tell me how they figured out the very latest they can leave their house in the morning and still be on time to school. That one always kind of worries me. I'm always envisioning students just speeding through town trying to get to school on time. Should leave early. Don't be in such a rush. Like another example, if you're having trouble thinking of something, would be if you like to cook. Whenever you follow a recipe, that's a procedure. You're using the scientific method in order to make something. And if you're anything like me, it takes at least 3 tries at a new recipe before it starts working out properly. You have a lot of null results. If you like video games, figuring out how to get to the next level, how to defeat the final boss or whatever. I'm not a video game person. But that would be something that you could write about because it all involves using the scientific method to solve a problem. All right, so the last part of this particular lesson involves doing a thought experiment that I call buttered cats. The inspiration for this particular thought experiment was a physics joke that I heard a long time ago, where it said, if buttered toast always lands buttered side down and cats always land on their feet, what do you get when you put buttered toast on the back of a cat? And the punchline is you get a levitation device because we got the butter effect trying to flip the cat over, and then we got the cat effect trying to get the cat to flip over, and so the two effects keep the cat spinning in midair. So to kind of get my students into the right mindset, I have a Beetle Bailey comic strip. So Sarge says, "Where's Bella? She's usually at your heels." Lady Sarge says, "Oh, some guys in the space program borrowed her. Something about an experiment to see if cats always land on their feet." And so I have a media clip. It's called Weightless Cats or Cats in Space, something like that. And it's actually a cat in the vomit comet. So what they're doing is they go way up to the stratosphere, and then they do free fall. They just dive in the plane so they can simulate weightlessness. So there we are. Cats floating because they're in free fall. That first bounce isn't very good. So they throw the cat again, and so the cat's trying to land on its feet, but because it's weightless, it's just spinning in space because of the conservation of angular momentum. And now that everybody's settling down, it's because they've come out of free fall. Okay, so here's the lab. So background. Recently, some very clever high school students discovered that a Mythbusters myth had been erroneously busted. Specifically, they discovered that toast would always fall buttered side down if the butter-to-toast mass ratio were high enough. While investigating the buttered toast phenomenon, one team of students decided it would be interesting to also investigate the myth that cats always land on their feet. To their surprise, they determined that while a cat will always land on its feet if dropped from a specific height, the cat's ability to land on its feet decreases if the height is changed significantly. So the objective is to combine these two separate observations, and I have some plotted data, and into a single question. And so I have some suggested questions. Does the butter mass ratio apply to other objects? So if you put enough butter on the cat. Or can the height at which cats always land on their feet be changed? It looks like I got a typo in there. So the first one is what I call the butter effect. And it says that once you have about 4 grams of butter, turn my laser pointer on, 4 grams of butter, it lands buttered side down 100% of the time. It does not matter how far you're dropping it from or what its original orientation is. It will land buttered side down 100% of the time. So this is the butter effect. And then the cat effect it says that does it matter what orientation you're holding the cat, if you drop the cat from 1 meter up, it will land on its feet 100% of the time. If you change that height to more than 1.5 meters above the ground, the cat never lands on its feet. Or if it's less than half a meter, the cat never lands on its feet. So with the key thing with always and never statements is that it means it doesn't matter what the orientation is. If you have the cat's feet pointed at the ground and you drop it from less than half a meter up, it's going to try to twist around and its feet will not land on the floor because it never lands on its feet. All right, so then they are supposed to design their own experiment, come up with their own combination of cat and butter. The example I usually give is if you put enough butter on the cat's head, will it land on its head instead of its feet? Or if you put butter on the cat's feet and you drop it from half a meter, will it land less than half a meter, will it land on its feet? Because now the butter effect is correcting for the cat effect. So they design their hypothesis, design a step-by-step procedure, predict the results, and then they have to answer some follow-up questions, which is actually the real graded part of the assignment. All right, so that's all I have to say about scientific method and buttering cats. So to wrap it up, the scientific method is an iterative process. You keep going through the loop and you change things one at a time to make sure that you're testing the right parts. Hopefully I've convinced you that everyone uses the scientific method, not just research scientists. Whenever you're trying to solve a problem, you're using the scientific method. Preliminary observations lead to questions. You go through the scientific method, which will eventually lead to a new discovery. That's why science is so exciting. Good experiments only change one variable at a time. You don't want to be changing too many things at a time because then if you actually do get a positive result of some sort, you don't know what it was that you changed that caused that result. Remember, data has to be analyzed. It's not enough to just collect it. You got to do something with it. And then if your conclusion indicates an unsupported hypothesis, revise your experiment, or revise your hypothesis, revise your experiment. Do it again. There's always more things to discover. There's never a wrong experiment. It's just you found out what doesn't make it happen. Okay, so that's it. Thanks for listening.